for AP Calculus on the topic of the ratio test and the root test. Continue. So the ratio test and root test, even though they're implemented differently, the conclusions are very similar, which is why I group them together. You're looking at whether the answer you get, if it's less than 1, both tests, the ratio and root test, tell you that the series converges. If the result is greater than 1, then the series diverges. If it equals 1, then these tests are basically inconclusive, and you'd have to use a different test to figure out if the series converges or diverges. So it says determine whether the infinite series converges or diverges and state what test you used. So the root test would work fine on this e to the n, but not really well on this, because the whole thing isn't raised to some exponent of n. So the ratio test, also a good clue to know when to use that is it tends to work really well in the problems with factorials, like we have n factorial on the denominator here. So let's try the ratio test on this one. So the way the ratio test works, you find the limit as n approaches infinity, and then it's the absolute value. Now, in a lot of these problems, the absolute value is not going to seem like it's necessary or changes the answer. But we'll go later on in this chapter, we'll go over some using the ratio test where the absolute value signs are very important. So if you get in the good habit of writing them down, even as you're doing these with the ratio test, then I'll help you to remember it, I think, when we go in using the ratio test when it is necessary as well. So the ratio test says you first substitute in n plus 1 into your formula. This is the formula for the nth term that we call a sub n. So a sub n plus 1 means wherever there's an n, you replace it with n plus 1. So that would give you e to the n plus 1 divided by n plus 1. It needs to be in parentheses factorial, like that. And then the formula says you divide by a sub n. But what you can do, since you're always dividing by a sub n, which is almost always some kind of fractional expression, then you know that's the same as multiplying by the reciprocal. So the original formula, so the n factorial goes here, and the e to the n goes there. So you can save yourself a step by just writing it multiplied by the reciprocal, because you're going to divide by the original one. And then you look for things that simplify before you try to substitute in infinity. So let's look at the n factorial and n plus 1 factorial. Well, n factorial, let's say n was 3. Well, 3 factorial means 3 times 2 times 1. And then that would mean n plus 1, that'd be more than 2, that'd be 4 factorial. So if we had 3 factorial divided by 4 factorial, 4 factorial would be 4 times 3 times 2 times 1. Notice what's going to happen, the 3 and the 2 and the 1 are all going to reduce out, we'll just be left with 4. And it's not even a factorial anymore. So the way we can represent that here is the limit as n approaches infinity, absolute value. So that's going to be, 4 is going to be on the denominator. In this case, that's n plus 1 without the factorial. That's what's left. Then we've got e to the n plus 1 and e to the n. Well, again, you can just put in specific numbers to help you out here. Then we've got e to the 7th divided by e to the 6th. Right? If n was 6, you can see you would subtract the exponents, just gives you e to the 1st. So that's one way to see you're just going to end up with e to the 1st here on the numerator, or just e. Another thing you can also do, remember all we were doing here is subtracting the exponents. So really another way you can figure that out is just take the n plus 1, this exponent, because they have the same base, minus this exponent of n, and you can see the n's would cancel out, leaving you with just 1 as your exponent. So either way, you just get e to the 1st or just e. And now you can substitute infinity into that. And e, there's nothing to substitute in there. That's just a constant around 2.7. And then the plus 1 is negligible when you add 1 to infinity. So So we get e over some huge number, so that's going to be very close to 0. And since our limit here is less than 1, the ratio test tells us that converges. So we can say this series converges by the ratio test is what we use. Well, and with the absolute value signs, you can see you'll never get anything negative. It's always going to be something from 0 to infinity. And if that's less than 1, like it is here, it converges. If it's greater than 1, it diverges. If it's equal to 1, inconclusive, and you use a different test. All right, let's take a look at the next one. Okay, on this one, notice we've got this whole thing raised to the end. So when you see that, that's a good clue to try the root test. So the root test, you also, it's similar in that you find the limit as n approaches infinity, just like the ratio test. But what you do is whatever that exponent is, the n, that's the same root you take. So you take the nth root of 1/3 minus e to the negative n to the n. And just like if this was a square root and the square, they'd cancel out. Cube root and a cube, they cancel. The same root with the exponent, those are inverse functions. They cancel each other out. So what we're left with is just limit as n approaches infinity. All that's left is 1/3. Sorry about the bell there. Minus e to the negative n. And let's substitute infinity into that, see what happens. So we get 1/3 minus e to the negative, there's where the infinity goes. And it's usually easier to analyze without the negative exponent. So this is 1/3 minus 1 over e to the infinity. But 1 over e to the infinity, that's 1 divided by some huge number that approaches 0, so you just have 1/3 minus 0. So we get 1/3. And just like the ratio test, the root test, you look at the same conclusions. Since this is less than 1, this tells us this converges. This series converges by the root test. Again, if it had been greater than 1, it would diverge. If it was equal to 1, it'd be inconclusive by the root test. All right, let's take a look at a few more here. All right, so here, notice the whole thing's not raised to some n exponent, so the root test probably wouldn't be a good choice here. We've got a factorial, so that's a clue again, probably the ratio test would work best here. All right, so the ratio test again, you find the limit as n approaches infinity. Absolute value. Remember, this is a sub n. So you first find a sub n plus 1, replace both, everywhere there's an n with n plus 1. So this is n plus 1 factorial divided by n plus 1 to the 100th power. And then you divide it by the original a sub n, which again is the same as multiplying by the reciprocal, n to the 100th over n factorial. And then you can simplify again the n plus 1 factorial and n factorial. Again, that's like having 3 factorial, 4 factorial, so you just be left with 4, which in this case is n plus 1 on the numerator this time. So the limit n approaches infinity, absolute value of, we'll have this n plus 1 on the numerator. And then n plus 1 to the 100th and n to the 100th. Well, let's see if we could simplify this. So let's just choose some simple numbers. Let's say n was 2. So this would be 2 to the 100th. And that would be n plus 1 would be 3. So that would be 3 to the 100th. Well, notice nothing there simplifies, right? Because they have different bases. So here, that part, not everything's going to simplify up. So we'll have n to the 100th, n plus 1 to the 100th. But then notice what we do have here, n plus 1 and n plus 1 to the 100th, they have the same base here, so you can reduce out one of those. So one of these can reduce out, just like if you had, in this case, n plus 1 was 3. So this is like we're having 3 to the 100th and just 3. So here, one of those could reduce out, right? You'd be left with 99, 3 to the 99 here. So you can do the same thing here. N plus 1 reduces out, and you're left with 99. So now what we've got is the limit as n approaches infinity, absolute value of n to the 100th, and now we've got n plus 1 to the 99th on the denominator. So then when you substitute in an infinity, you get infinity to the 100th. And again, the plus 1 is negligible, so this is like infinity to the 99th. So you can see that reduces, those cancel out, we're just left with 1 infinity, which is greater than 1. So that tells us this diverges by the ratio test. All right, let's take a couple more here. On this one, notice this whole thing is raised to the n squared power. So it doesn't always have to be to the nth. It could be something else that involves n here, n squared. So you can still use the root test. It's just when you find the limit as n approaches infinity, since it's the n squared power, that's the same root you would have to take of the whole thing. 5 plus 4n plus 5n cubed over 4n cubed plus 6n plus 1 to the n squared. And again, because we're taking the same root as the exponent, those are going to cancel out. So if n was like 3, for instance, this would be 3 squared, this would be to the 9th power, and this would be the 9th root. Whatever it is, if you use the same root as the exponent, it's going to get rid of that. And then it simplifies to be a normal limit, where all we're left with is 5 plus 4n plus 5n cubed over 4n cubed plus 6n plus 1. And then when you substitute in infinity, notice on the numerator what's going to matter is the term with the highest exponent, let me spell on this, 5n infinity cubed, and the denominator, the one with the highest exponent, the 4 infinity cubed. And here the infinities completely reduce out. So we're left with 5/4, which is greater than 1. So that tells us it diverges by the root test. Sorry, not by, by the root test. Okay, let's look at one more that's a little more complicated here. So on this one, got a bunch of things going on. Even though this is to the nth power, the whole thing is not. So let's try, it's got some factorials, let's try the ratio test here. So we'll have the limit as n approaches infinity, absolute value. Again, remember this is a sub n term, the formula for a sub n to find any term here. And first we have to plug in n plus 1 for, in this case, there's 3 different n's. So here we have n plus 1, but then we're adding 2 to that. So see how that's going to become n plus 3 factorial? Then this 2 factorial just stays there. There's no n's in that. Then the n factorial, we plug in n plus 1, that's n plus 1 factorial. And then this 2 to the n becomes 2 to the n plus 1. And again, the ratio test says, remember, ratio is just another word for a fraction. So that's why we're dividing by, it's the ratio of this one, n plus 1, to the a sub n. And instead of dividing by the original one, it's the same as multiplying by the reciprocal. So the 2 factorial, n factorial, 2 to the n, over n plus 2 factorial. Alright, so let's see what we can see that reduces here before we substitute anything. Well, first, notice 2 factorial, that's a constant. That's really just 2 times 2. So those completely reduce out. Then we've got n plus 3 factorial and n plus 2 factorial. So again, when the factorials are one more than each other, that's just like, let's say this was 5 factorial and this was 4 factorial. One more than that, then this would be just left with the 5, or in this case the n plus 3. So we'll have n plus 3 left there on the numerator. And if you want, as you go, you can kind of cross that out. That one's gone there. And then we've got n factorial and n plus 1 factorial, same idea. This is one more factorial than this one, so the n factorial is going to go away, and we'll just be left with n plus 1. And then we've got 2 to the n and 2 to the n plus 1. Again, subtract the exponents here. This is one more than the exponent, so we're just going to be left with a 2 on the denominator. And then n plus 1 and n plus 3, that doesn't simplify at all. This is just 2 more than that. This would be like having, let's say this was 3 and this was 5. This wouldn't simplify at all. So we can add the limit. And then we can substitute infinity into what's left. So we've got infinity, the plus 3 is negligible. The plus 1 is negligible. But multiplying by 2 is not. Because notice, then the infinities reduce out, and we're left with 1/2, which is less than 1. So that tells us this converges by the ratio test. And that concludes notes for AP Calculus on the topic. The ratio test and the root test continued.